I'll start in the new year. This will be the curve. It will not be symmetric because in lab when you do it, no, it will not be symmetric. We have maximum current. That maximum current I'll denote by I naught. I naught or any other symbols, I naught. What I plotted is IRMS and this is the frequency. This is a resonant frequency. This is upper bandwidth, upper cutoff frequency, lower cutoff frequency, and this quantity is called as a bandwidth here. This IRMS only is what I'm plotting. This is the maximum value of that current. No, so we'll define the sharpness of this curve. So that I have to derive expression. How it depends on the resistance. Already I shown graphically. Now mathematically, I'll bring an expression and I'm going to show that the sharpness in fact depends upon the resistance here. So we'll proceed like this. So I'll define quantity called as a quality factor. Quality factor, this is defined as resonant frequency by bandwidth. So the symbol is used Q, capital Q, resonant frequency F naught, and the bandwidth is what? BW. Or this you can write only delta F. What is delta F? F2 minus F1. So what is the bandwidth? This we can also write it as delta F here. So now you can see this, the sharpness here. If the bandwidth is less for a given resonant frequency, then Q will be more, then sharpness will be more, no? You try to see this. If there's a bandwidth, and you can look at here, there's a bandwidth. So as the bandwidth increases, the sharpness of the curve will decrease here, or the sharpness of resonance curve will decrease here. So therefore, the quality factor we just define as resonant frequency by bandwidth here. First of all, you have to ask question, sir, what is the quality factor? It's a measure of how sharp the resonance curve is. It's a measure of how sharp the curve is. Then, sir, why do the sharpness again you are bringing? What is the use of this sharpness? Current maximum, it's over. Why the sharpness here? So if you go for the application, suppose say, let's take that one. I think you know FM now. So let's take that 92 megahertz is what? The frequency of a station. Then the song, music, what all, then it's audio signal. So how much frequency of that everything will be? 20 kilohertz. So therefore, so what should be the bandwidth of that particular station? The bandwidth of the station should be of 20 kilohertz. Or let's put 0.5 megahertz. In this 0.5 megahertz, what happen? I'll put all the information. What is information? What all I speak? The music, what all that in the FM station generated, no? So that everything what happen will be accommodated in this particular range. So therefore, now what is the bandwidth? 92.5. Where the station will be available for us will be 91.5 megahertz. So this everything will become bandwidth here. How much bandwidth will become? The information to put is we need this much of here. So 0.5 and 0.5. 1 megahertz will become bandwidth here. 92 megahertz is the F naught. 92.5 is the upper cutoff frequency. 91.5 is the lower cutoff frequency. Within this range, the information of station will be available. Later on in communication chapter, we are going to learn in detail. Okay, got this one now. So now to tune for this particular thing. So what I do is like, I should design my radio, that particular mobile in which FM circuit is there, it should able to grab this much of the signals here. So then why sir, why you are bringing I naught by root 2? So when a signal arrives at a station, or so like if it's a mobile or anything, that one. So what is the requirement is, all those signals, means the signal which is equal to resonant frequency, it will have maximum power. What about the power of these signals? Will be, I think this particular frequency is having maximum power, no? Current is maximum. What about here? Power decreases. Then which all set of signal frequencies I can select? Not only just this, along with this maximum power signal, you can select all the signals which are having power at least half of the maximum. At least half of the maximum means what it will become. So let's go for calculation. So what is the maximum power? P naught is equal to maximum power. Why only I naught by root 2? Sir, you are cutting that from there. Why you are finding a F2, F1? So the maximum power P max is equal to I naught square by R. Then I'll consider all those signals, at least they should have power half of the maximum. So which signals will be useful for an application? This will contain information. The information will be spreaded here. The information will be spreaded everywhere from 0 to almost you can say infinity. Then sir, which signal I should consider? The one, this is maximum, this having maximum power. Along with this, you can even consider those frequencies which are having power half of the maximum power. And those frequencies which are having power less than maximum power, they'll not be useful for application. This is one, practically they noticed it. That's why they made a rule. So when you're designing a circuit, what will happen? What are the range of frequencies you should consider? Maximum power and the frequencies surrounding the maximum power where they're having power half of the maximum value. Got this one? So let's come for this half of the maximum. So what is the value here? This will become, I'll shift it down. Now this should be equal to I square R. So what is I is equal to I naught by root 2. Got now? So now for that, after getting this one, so what I should do here, after plotting this graph, I locate maximum current. I know I naught value. I know resonant frequencies. Got it now? How to get I naught? I naught depends on what? Again, what is I naught? I naught depends on what? I'll keep this circuit in hand. Otherwise, you'll not understand anything. You should tell me I naught depends on what? I naught depends upon this applied VRMS and R, no? Of course, this is RMS value only. I'm just calling it I naught. So this I naught in fact depends on what? So this VRMS, for our convenient purpose, I'll write only V. VR. And I can measure this I naught. I know resonant frequency. Resonant frequency depends on what? So after plotting graph, I can identify F naught. Okay, got this? And I know I naught. Then I will just move down along the current axis here, where current will become half of the maximum. So why only I naught by 2? Why not? Why don't you write I naught by 2? You should pick up only those signals, frequencies where the power is half of the max, not current is half of the maximum current. Able to understand the logic? So all those frequencies where power is half of the maximum power, they are useful for application along with resonance. This is the main thing. Along with this, these frequencies also are going to help us a lot. What about, sir, these frequencies? They will not help us in application. Practically, they made this a rule. Practically, they say like these set of frequencies, they are going to help us a lot. So it should be I naught by root 2. From there, what I'll draw a horizontal axis. It will cut the curve at 2 points. From there, I'll drop a vertical. These I'll call this as upper cutoff frequency. This has lower cutoff frequency. And I'll measure the width. There's a bandwidth. The bandwidth, the resonance frequency by bandwidth will become quality factor. This is something very important. What is the quality factor? How well the receiver circuit is able to receive the best signal. Means here, sometimes we get a noise, no, or we are unable to hear the station properly. What is the problem arise? The quality factor of the circuit at that given instant was very poor. Due to many reasons, it get disturbed here. So in all communication, television, mobile, satellite, this circuit is widely used here. Okay, let's come for further that one. So I want to say that how it depends on R. I think that was our question. No? I brought this I naught. So let's come for this one. So what is I naught equal to? This will be, so what is I is equal to? What about current here? I naught by root 2. This I shall I write in another way? V by root of R square plus XL minus XC whole square. Now you should really ask me, sir, from where you brought this. At resonance, what is current I will be Vrms by Z. If it is not at resonance, you write Vrms by Z, no? Because what is this current? This current which is flowing here, current I is flowing is not at resonance. I naught is the current which is flowing at resonance. Further, what is I naught? We can write it as I naught is equal to V naught R I naught by V. So we can write it as so root 2. So I'll do one thing. This will be 1 by or V by I naught. Let me keep here. So what is V by I naught? Vrms by I naught. This should be equal to R only. According to this equation. So further this equation will, let's put in order. I need a lot of space here. Let me do it here only, everything. No. So V by I naught, I'll write it as R. So R is equal to root 2R is equal to root of R square plus XL minus XC whole square. Now, books are not given in detail, that's why I'm just showing it. So this will become 2R square equal to R square plus XL minus XC whole square. So this will become R square is equal to XL minus XC whole square. XL is this R equal to omega L omega C. Let's solve this. So we'll get a quadratic equation R equal to omega square LC minus 1 by omega C. Omega square minus omega R by L plus 1 by LC, all set equal to 0. Check one's calculation. This will be negative only. Then it's a quadratic equation. We'll solve for omega. So omega will be 2 is missed. Okay, this will be only R by L plus or minus R square plus L square minus 4 by LC. So one angular frequency I'm going to get, that is what? Omega 1, I'll write it. R1L all divided by 2. First angular frequency omega 1, R1 R by 2L. The other frequency will be R by 2L plus so I got omega 1. From omega 1, what you can bring? You can bring 2 pi f1. And we have to calculate the bandwidth, no? How to calculate the bandwidth? So let's come back to the formula. I'm interested in this. So I got omega 2 and omega 1. And this is f naught is there. So let's come back to the everything I'm showing it. Just see once what all we did. Let's come forth. Let me substitute that value. So I got this omega 1 and omega 2. I'm going to substitute that one here. And I know f naught also. From that, I'll bring expression for the quality factor in terms of the components of the circuit, like R, L, C, how they'll depend on that particular thing. Shall I proceed here, no? How to calculate bandwidth? Say bandwidth is f2 minus f1, no? So let's calculate the bandwidth here first. This is the initial calculation part. Bandwidth BW should be equal to f2 minus f1. Or this will be omega 2 minus omega 1 what should be this quantity should be equal to 2 times of r by 12 get cancelled, so 2 times of under root of r square plus l square plus 4 by lc. The two parameter is two. I to send it inside. Denominator 2 has to be adjusted, no? Just 1 minute. I'll adjust 2 also. So this will become 4. This will be only 1 by LC. Why it should be? Because this 2 is what for under root also should be adjusted. This will become 4. Yeah, fine. Now look at this quantity. We have this much here. So what is the value of bandwidth? Bandwidth, I got this much. Bandwidth equal to f2 minus f1. We ended up this one. Let's come for, do we know resonant frequency? Yes, it will be.
Sir,
Yeah.
omega 1 is negative.
Why negative?
R by 12 minus under root R square by 4L square. So the first term we have inside the under root, we have that term squared plus something else. So the second term will be greater than the first term.
Magnitude, no, it is. Magnitudes.
So
No?
when we are subtracting, we have to take mod and subtract, no sir. We have to subtract the magnitudes.
Okay, that r by 2 will get cancels, no?
No, sir, the under root term will get cancelled then.
Why?
We should write
Negative.
omega 1 as under root r square by 4l square plus 1 by lc minus r by 2l, not the other way around.
Omega
And
2 is
then,
this much. Omega 2 is this much. Then minus of this. Why this is? There's a magnitude, no? This omega 1 is some value that depends on this one.
yes, sir. Now, what expression you wrote, you'll get negative value there. We cannot subtract then.
No, omega 2 minus omega 1, I'm doing this. Root minus of minus will become plus.
Sir, if we can write omega 2 minus omega 1 if omega 2 and omega 1 are positive. But omega 1 is negative. So we should like write it in the reverse order and then subtract it.
Frequency is, how frequency is negative here? Huh?
Sir, you see there, sir, you got negative value. R by 2L minus this thing will be negative. Sir, actually what happens is when you wrote R square equal to XL minus XC whole square,
Like plus or minus, sir.
that you'll get two roots, plus or minus. So from there you'll actually get four roots. Out of that, two will be positive, two will be negative. Those two
Okay,
we
we'll
should
do one thing.
remove.
I'll just wind up, then we'll see whether we are right or wrong. Huh? Mathematics is correct or physics is correct. Huh? Okay, now this will be, now 1 by LC, you can, this will be, this you can neglect the bracket term. So we'll end up with this 1 by 2 pi 2. So this will be R by 2L, I'll bring outside. So here 1 by LC will be very much greater than 1. So this will become negligible. So the approximate what we are bringing like this here. So finally how much it is? The bandwidth is equal to, we are getting 1 by 2 pi R by L. Let's go for quality factor. Quality factor we define F naught by bandwidth here. F naught by bandwidth. What is F naught? F naught again, this should be, so I'll substitute as it is. So bandwidth is equal to how much? 1 by 2 pi R by L. So this will become 2 pi F naught R by L. So this will become omega naught. Or this will become omega naught L by R. This is a formula which we brought it. And what is omega naught into L? Should be the inductive reactance. And at resonance, we know when F equal to F naught, XL equal to XC in terms of mod. So the quality factor, we can also write it as Q equal to XC by R. So quality factor, how to increase the sharpness of resonance? We have one option. What is that? This is omega naught, I'm not going to disturb. L, very difficult. R is variable. By varying R, we can control the sharpness. So therefore, where do we see this? I think you go for the even the Tata Sky remote, or you can say any other DTH. Fine tuning, they say, no. Omega naught, with that you are selecting the channel. Again, to avoid any disturbance, what happen? We do fine tuning. What is that fine tuning? The fine tuning is varying R. By varying R, what happen? Will make Q by decreasing value of R, Q will become high. Q becomes high, what happen? The unwanted signals will be eliminated. Then we'll get a program which will be like a without any disturbance. Same thing in the FM radio also. You see that 99, 92 megahertz. At 92 megahertz, you'll get a signal. Then if you just move right or left side of 92 megahertz, no, the disturbance will get added up. And again, some FM sets, if you purchase no good FM sets, you'll get fine tuning. Fine tuning is what? This R. 1 by LC, this quantity should be negligible, no? Or LC will be very much greater than 1. Let me put like this here.
How did you make that assumption, sir?
practically.
Sir, in some of the numericals, what we solved, L and C are
Ju-
in
ju-
like micro levels.
just listen. Nothing. There's only in resonance we do like this. Not every problem. Don't generalize it. Hmm? So in practically, when I go and check it, no, the formula which we have brought it, it is satisfying almost 99% of the performance. This I know approximated, but this is widely used in designing of circuits here. So now, how to increase the sharpness of resonance? Earlier, what we taught is sharpness of resonance depends on what? Just I gave a curve. So as you increase R, the curve what pen will become less sharper. As you decrease R, the curve will become more sharper. So how do you can plot curve like this? I can justify the reason from here. You look at the quality factor, it is inversely proportional to resistance here. So first of all, sir, what is the quality factor? What do you mean by Q? It is a measure of sharpness of resonance, or how good it is in selecting, how good it is in selecting the desired signals. This is something very important in communications that for us it's only just mathematics, because we never understand what you mean by selecting all that particular thing. How good it is in selecting the desired signals by a receiver circuit, by a tuning circuit it is called as. Tuning, I think tuner. So in television also we tune, no, for different channels. Then to avoid any disturbance or any other thing, no, the value of R should be adjusted. By using omega naught, what happen, will select a desired station, desired program. Then how to minimize the disturbance in that program? By varying R. By decreasing R, yes, the disturbance in the program will get eliminated. This is actually the basic idea of this one. So either the sharpness depends on what? Omega L, or we can also write another formula. So I think I'm writing all set of formulas at one place. Or we can also write it as XL by R. So from XL by R, what you can write it as? Omega naught L by R. Or another formula, XC by R. See, I don't adjust omega naught, because omega naught and C are fixed here. I can't change C and omega naught. If you vary C, omega naught will change. So therefore, how to eliminate the disturbance? By varying R. By decreasing R, the Q will increase, the sharpness will increase. So like this, the method is what brought in the communication circuits here. So can we write in another form also? I'll adjust IRMS, I into XL, I into R. What is I into XL? VL, and this is VR. Or we can also write it in another way. Q is equal to XCR. So how to measure the sharpness of resonance? The voltage drop across the inductor to that across the resistor. I think this will be more easier to measure, no? How to measure the voltage drop? Directly connect voltmeter across inductor and connect one AC voltmeter across the resistor. Take the ratio of that. That will determine how sharp is the curve is. See, I'm telling you this one. I am not going to change the resonant frequency of the circuit. This F naught is as it is. By varying R, I can change the shape of the curve. But the what happens to the sharpness? What will happen to F naught? F naught will not change. By varying R, F naught will be fixed here. Where the current should be maximum, at F naught only will be maximum, that will be maximum. But the, look at the shape of the curve. This shape depends on R. That's what this particular graph I brought it. I brought it here. So now how to measure that quality factor? directly measure potential difference across the inductor resistor, take the ratio of that, you get quality factor. And then how these omega naught, omega 1 are related. So one more relationship I brought it, just you cross verify it. This one more formula is there, just do remember. You can, because we know omega 1, omega 2, from that you check it, you'll end up with this one. The cutoff frequencies are related to the angular frequency by this particular formula, or F naught you do have problems in books. So just if you know formula, you can manage here. So you know F1, F2, how I brought it. Take help of that and you can get this relationship by doing some approximation. Then after this, what is another way of defining quality factor in terms of energy? Q, it is defined as 2 pi into energy stored by energy dissipated per cycle. All this is, I think nothing wrong here, no? This is all per cycle. So from where I'll do one thing, I'll adjust one more I square. I square XL is what? Reactive power. I square R is what? The dissipative power. Energy, reactive energy. Energy stored means not total, reactive, anything. Either you take uh, inductive reactive power or capacitive reactive power. So how we define energy stored per cycle by energy dissipated per cycle, because what all current flows to the resistor will be dissipated. What all the current that flows across the inductor or capacitor, that is what the energy that is stored here, and it will be returned back. So energy stored per cycle by energy dissipated per cycle. I think here is what the basic idea, it will come into picture now. So when the quality factor will be good, when the energy dissipated per cycle if it is less, then the quality factor is supposed to be I. And this energy stored is what? Like reactive power. Stored, I'm using what? Stored means the circuit will exchange energy twice. The reactive elements will exchange energy twice with the source, no? In a cycle. So same thing happens here. So the energy stored per cycle by energy dissipated per cycle. They may ask this one here. You have to be very careful with this particular formula. So for any like a tuning circuit, we prefer Q to be very high. So this is about the theoretical thing, just only say mathematical way we are learning it. When we go for communication chapter, there what you are going to learn in detail. So the quality factor of that RC circuit matters a lot. So I'll suggest you, like, what is the actually meaning of this? Suppose this is antenna, this one. So the antenna, this wire will have a resistance, antenna. Then this is a capacitor, this is an inductor. Then this is the circuit here, which I'm going to connect to, or say loudspeaker or anything, let it be that one. Now several station programs will come. So this will be, say, 88 megahertz, 90, 92, 96, 100 megahertz. All these are in megahertz. Then have here, LC, that one. I'm going to vary the C. By varying C here, what I do, I'll select a desired station. So there is station 1, station 2, station 3, station 4, station 5 stations are there. All 5 stations, they are transmitting their program. And what we are interested to hear any one program. How to select the desired particular program. I think you know FM. Suppose you are listening to 92 megahertz. Then when you're listening 92 megahertz, what happens to programs of other station? Will they stop transmitting? They say like a so-and-so person studying in Sri Chaitanya College in DD Colony is listening this particular station, so we should switch off all other stations. Is it like that? No. Whether you listen or not to their program, everyone will transmit their own like a programs at a frequencies 88, 90 megahertz, 92, 96, 100 megahertz. You want to listen for 90, 92. So what you're going to do, you're going to adjust the value of L and C such that you'll get this much. So here you're going to vary the C. Then once the frequency of circuit becomes equal to 92 megahertz, then what happens, that particular program station, what happen, only will have maximum current corresponding to that. What about this 90 megahertz? It's like a signal will come and strike the antenna. Then what happen, current due to this particular frequency signal will be very less because it's not at resonance. So when current will be maximum, only when the frequency of incoming signal becomes equal to frequency of source, frequency of circuit. Now this is a circuit. And now what is the source? There are 5 sources are there. S1, S2, S3, S4, S5. Is as good as like 5 sources are applied to the circuit. Then I want to listen only for this 92 megahertz. What I should do? I'll adjust the capacitance of circuit in such a way that the resonant frequency will become 92 megahertz. Then the current due to this signal only will be maximum. What about current due to these signals? Will be there, but they'll not be maximum. Any reason for that? At resonance. So how do this circuit? It will appear like this. So our circuit is designed for this one, 92 megahertz. Then what about the response curve of other things? Of other circuits will be very less. The current due to that will be there. What will be that? We are not bothered that one. So now you can look at this one. So when the frequency of circuit becomes 92 megahertz, only current due to that will be maximum, no? So here what when I'll get all the signals, but current only due to that 92 megahertz will be maximum. Then what I do is like the one which is having maximum current only, I'm going to filter it out. Then that will be amplified and given to us. We are able to listen only that station. What happens if you listen all 5 programs at a time? I think it'll become noise, no? In a classroom, if all 5 students asked out at a time, we call it the noise. So what I should do? I should request any 4 students to stop talking. Later on, let only one talk. The circuit is called like a selective circuit. With the help of this series resonance circuit, what I'm able to do, I'm able to select a desired set